Hey there everyone. In this section we want to keep working with compression ratio just a little bit more, but what we want to look at are the effects of things that you do when you do a rebuild that change your compression ratio, either on purpose or by accident, and how those effects kind of pan out. So let's take a look. First of all, when you make a change to anything inside the combustion chamber, you're probably going to change your compression ratio. And so I'd like you to think about what are the 5 common things that happen during an engine rebuild, either on purpose or unintentionally, that will change your compression ratio. Well, you can think about those for a little while, but you'll probably reach the same 5 conclusions if you know how an internal combustion engine works. Of course, you might oversize the bore, that is to say, overbore it um, and put in larger pistons, and that typically causes the compression ratio to go up because you're stuffing more air and fuel into the same space at the top of the cylinder. You can change the cylinder heads. That's either because you got a head that flows better or you're replacing one that's cracked, any number of reasons, and that can cause the compression ratio to go up or down depending on the volume of your new combustion chambers. And likewise, you might change pistons, either because a piston got burned or doing a rebuild and just putting in a new set of pistons. And again, that can go up or down depending on the volume of the piston relief. A common problem that engines that have overheated has is that the block or the head will warp. And so if you machine the top of the block or machine the bottom face of the heads, that typically reduces the amount of volume for compressed air and fuel. That causes your compression ratio to go up. And of course, the last thing that's very intentional and the least common is you can install a stroker kit. And usually a complete kit will have pistons that take into account the fact that your piston is going further down in the bore, but ultimately your compression ratio could go up or down depending on the original engine specs. Okay, so all I want to do is go through 3 common changes with you, 3 examples to show you how those compression ratios will change. First of all, from part 2 of our last lesson, a Ford 302 has a 4-inch bore, which means the radius is 2 inches, a stroke of 3 inches, piston to deck clearance of 6 thousandths, gasket thickness of 35 thousandths. Pistons have 6.4 cc reliefs, and heads that have 60.5 cc combustion chamber volume. What is the compression ratio? We did that problem in part 2 of the lesson in compression ratios, and we got 9.2 to 1. A little refresher on that. We took volume 1, our combustion chamber up at the top of the cylinder. We converted it to cubic inches because all those units have to match. Step 2, our gasket volume, number 2, right below that. We took pi times the radius of the bore squared times the thickness of the gasket, and we got 0.44. Step 3, right below the gasket, is the piston to deck clearance. That was pi times the radius of our bore squared times the piston to deck height, which is 6 thousandths, and that gave us 0.08 cubic inches. And then we took volume 4, which was our piston relief. That was 6.4 cc, and we just converted it over to cubic inches. We got 0.39. Those are our 4 small volumes. We added those up to get 4.60 cubic inches. That is our clearance volume. Volume 5, the big one in the middle, that is our swept volume that we use to get displacement, pi times the radius of the bore squared times the stroke, and that turned out to be 37.70. Your compression ratio is clearance plus swept divided by clearance, which turned out to be 9.2 to 1. We can go through that in more detail. Go back and watch part 2 of the lesson on compression ratio for a more detailed explanation there. Our question here is, what if this engine gets bored 40 thousandths oversize? That's going to change our compression ratio. We don't really need to work this from scratch. What's going to change? Well, if our new bore gets bored 40 thousandths oversize, our bore is going to be 4 inches plus the new 40 thousandths oversize that we're boring it. And so our new bore is going to be 4.040 inches. And all that matters from that, if we divide that by 2, our new radius will be 2.020 inches. So let's get these new calculations based on the new radius. Combustion chamber volume, that won't change. That's okay. Our gasket will change a little bit. We need to replace that with 2.020, which raises this from 0.44 to 0.45, so not really much change there. As it turns out, our piston to deck clearance doesn't change at all. That's okay, even though the radius does grow. It's not enough to affect our calculation. And our piston relief doesn't change. Now we might swap out different pistons, but if our relief volume doesn't change, changing the bore won't automatically change that. And so that means that our clearance volume changes from 4.60 to 4.61. Not much change there. The big change comes in our swept volume. If we change the swept volume by overboring it, that's going to have a pretty big impact. Our new swept volume, it's no longer 37.70, it's 38.46. And so our new calculation is 4.61, our new clearance volume, plus 38.46 divided by 4.61. That's our new clearance plus our new swept divided by our new clearance. And that's no longer 9.2 to 1. Turns out to be 9.3 to 1. Now you might say, well, that's not much of a change in compression ratio. And you're right. If that's the only engine modification that happens, you really don't need to worry about your compression ratio changing. It'll go up, but not by very much. Okay, here's another example that shows a little bit more severely what can go wrong. A Caterpillar 1693 TA engine has a bore of 5.4 inches, a stroke of 6.5, 30 thousandths thick gasket, and 10 thousandths deck height. Combustion chambers are 16 cc's, piston dish 138 cc's. We did that problem in the last lesson and we got a compression ratio of 15.4 to 1. Here's how we did it. Quick refresher. We converted the combustion chamber volume of cc's into cubic inches. Then we took pi times our radius, which is half of the bore of 5.40. Pi times the radius squared times the gasket thickness that gave us our gasket volume. Right below our gasket is our piston to deck volume. Almost the same, pi times radius squared times the piston to deck clearance, and that gave us 0.23. Then we took our piston relief of 138 cc's. We converted that to cubic inches and got 8.42. Add those four small volumes together, we got a clearance volume of 10.32 cubic inches. Then we find our big swept volume, which was pi times our radius squared times the stroke of 6.5 inches. That gave us 148.86. And if we add our clearance plus our swept divided by our clearance, that's how we got 15.4 to 1. If you want more details on that, you can go back and watch part 2 of the lesson on compression ratio, and that goes through that exact same example a little more slowly. Our question is, what if we put on new cylinder heads that have 32 cc combustion chambers? So we're going to swap these out for combustion chambers that are a little bit bigger. Well, of course, of these 5 volumes, that's the only one that changes. Volume 1 gets larger, so instead of 16 cc's, it is now 32 cc's. And so instead of 0.98 cubic inches, we get 1.95 cubic inches. All these other volumes stay the same. Thank goodness we don't have to recalculate anything there. But our clearance volume will also go up, and that increases to 11.29 cubic inches. Our swept volume does not change. So now our clearance is 11.29 plus our swept, which didn't change, of 148.86, divided by our new clearance of 11.29, and that gives us a new compression ratio of 14.2 to 1. That's a dramatic drop in compression ratio, and that engine is going to produce a lot less power and run at a much, much cooler temperature. There's a lot of problems with that change. So changing a combustion chamber, or a piston for that matter, can have a huge impact on compression ratio. Okay, and one more case to wrap this up. A VW TDI engine has a 3.130 inch bore, 3.760 inch stroke, 25 thousandths gasket, and 20 thousandths piston to deck. Piston reliefs are 8 cc's and the combustion chambers are 12 cc's. Let's calculate the original compression ratio and the new compression ratio if the block has 12 thousandths milled from its deck. Well, for starters, we'd work through our 5 volumes. One, the combustion chambers are 12 cc's. We convert those to cubic inches so that everything matches. We get 0.73. Our bore is 3.13. Divide that by 2. Our radius is 1.565. That means our gasket volume is pi times our radius squared times our gasket thickness of 0.025. Gasket volume is 0.19 cubic inches. Right below that is our piston to deck clearance. Almost the same idea, pi times radius squared times the piston to deck height, and that is 20 thousandths. We get 0.15 cubic inches. Volume 4, our piston relief volume. It's 8 cc's. We just convert that to cubic inches. It turns out to be 0.49. And if we add up those 4 small volumes, we get our clearance volume, which is 1.56 cubic inches. We're almost done. Our big volume in the middle, our swept volume, is pi times radius squared times the stroke. That turns out to be 28.93 cubic inches. If we wanted to know the displacement, we could multiply that by the number of cylinders. But then our compression ratio is our clearance of 1.56 plus our swept 28.93. Get that total, and then divide by 1.56, we get 19.5 to 1. That's our original compression ratio. Now, what's going to happen when we mill 12 thousandths from the deck? Is the compression ratio going to go up or down? Well, it's going to go up. The question is, how much will it go up? If we take our original piston to deck clearance and take off 12 thousandths, we're not going to replace this with 12 thousandths. We're going to subtract 12 thousandths from that, and that means our new piston to deck clearance is 8 thousandths of an inch. And so the only one of these 5 volumes that changes is our piston to deck volume. And if we recompute that, this turns out to be 0.06 cubic inches. Now we can re-add our combustion chamber, our gasket, our new piston to deck volume, and our piston relief volume, and it's going to give us a new clearance volume. It's no longer 1.56. It's now 1.47 cubic inches. Good thing is our swept does not change, so we can go back here and replace our original clearance with our new clearance in both spots. And our new compression ratio does in fact go up. It goes up to 20.7, so that's a pretty big bump because this volume has got fairly high compression ratio and not much volume for unburned air and fuel to begin with. So we see a pretty quick climb in our compression ratio due to a relatively small change. There you have it. So be aware that those 5 common engine modifications can alter your compression ratio, sometimes a little, sometimes a lot. But something to be aware of anytime you're making one of those modifications. So your problems for today will have you computing some compression ratios and the new compression ratios when you make a change. So there's really nothing new about the process, just more information about compression ratios. Let me know if you need help, and we'll see you in our next topic.